Hello everyone. So I will be the first facilitator, and it's my honor to present Cheng-Li from National Tsinghua University in Taiwan, and he's worked with this reconstructing momentum spectrum of muon in a range counter system, and he's been supervised by Professor Aoki. According to the abstract, the range counter system will work as a kind of detector to identify incident particle and measure their spectrum in the upcoming COMET experiment. And since I'm from an environmental engineering background, I'm not so well versed in this nuclear physics, so I will give the word to Cheng-Li to present his research, and I'm sure we learn a lot. So, are you ready?
Yes, okay, thank you.
Yeah.
Okay, so let's start. Okay, so hello everyone, I'm Cheng-Li Chen from National Tsinghua University, and today I want to share my current research, the reconstructing momentum spectrum of mu minors in a range counter system. So first, I want to introduce experiments that is related to our research. So it is the COMET experiment at J-Park. And the goal is to search for the neutrino-less muon-electron conversion. And it is expected to probe new physics beyond the standard model. And their experimental sensitivity goal is in order 10 to minus 15. And besides, a commissioning called phase alpha will be conducted in this year. And phase alpha is a part of the COMET experiment, and it is to measure the momentum spectrum of elementary charged particles, such as electron, muon, and pion. And in our research, we mainly focus on the mu minors. Okay, so the first question is that how can we measure the momentum of charged particles? So here we can utilize a physics phenomenon to do so. So for example, we can see this graph. If we place a median, here we call the degrader in this position, and then we let the charged particles, here we use the mu minors as an input. So we will see that the mu minors will lose their energy in the median. So they will get decelerated or stop in the median. So as we can see in the following graph, as the incident momentum of the mu minors gets larger, then it means that the stopping position of the mu minors will get more and more far away from the original incident point. As a result, we can conclude that from stopping position in the median, then we can know the original incident mu minors momentum indirectly. Okay, so but in real experiments, how can we measure the stopping position of the mu minors? As a result, we will use the range counter system in this experiment. So it is composed of degrader, absorber, and two scintillator. The degrader is used to decelerate the particles, and absorber is mainly to stop the particles. And scintillator is used to detect the events. So as we can see, if we have an original uniform momentum of the incident mu minors, and we can adjust the degrader length to certain thickness, and then we can stop a specific momentum region of the original mu minors. And such momentum region of the mu minors will be stopped in the absorber. And we can count how many entries are there in the absorber. And then we can plot the black dot as shown, for example, like here. So if we can just change out degrader length, and then we can plot a set of black dots as our reconstructed point, and then we can get the reconstructive momentum. So the red line is our original input momentum, and the black dot is the reconstructive momentum. And this graph is in the preliminary study. So we can see that there shows a problem that in the high momentum region, we have reconstructive entries has been underestimated, as shown here. So the motivation for our research is to analyze this discrepancy and try to find out why and try to figure out this problem. So in our research, our method is by using the G4 beamline program. It is a simulation package. And since the charged particle in the median, the energy loss is a statistical process. As a result, we just use this program for the pure Monte Carlo simulation, which is to check each single incident particle for each event. And the right-hand side is the experimental configuration in our experiment. Okay, so let's talk about the results from our simulation. So first, I want to introduce a physics quantity called the stopping-absorber ratio, as shown here. So it describes how many entries are actually stopped in the absorber comparing to the total entries. So if every entries are stopped in the absorber, then our ratio is 1. And this is our y-axis. So as we can see in this graph, we have different kinds of incident momentum as shown in different colors. And we can see that for each kind of incident momentum, we can always find out a proper degrader length in order to maximize the stopping absorber ratio comparing to the corresponding momentum. So as shown here. And we can just focus on seeing the maxima point of this curve. And we can see that in high momentum region, for example, here is above the 90 MeV, then we can see that the maxima is getting decreasing. And this tendency, we believe, is the reason that result in the discrepancy when we are trying to reconstructing the momentum. But why is this thing happens? So we need to have an analysis.
So there's been 5 minutes now.
So
please continue.
first I want to, yes, okay. Okay, yes. Okay, so first I want to introduce a concept is that for a limited thickness of the absorber, then the ability to stop the particle is also limited. So for example, as shown here, if we have incident particles mu minus with uniform spectrum, uniform momentum, then we let them input into the absorber. And then we can set only the mu minus particles that is below certain momentum threshold can be stopped by the absorber. And we call this area the momentum acceptance of the absorber. And we should know that for better measuring resolution, the absorber thickness should be as thin as possible. As a result, in our range counter system, the momentum acceptance is limited. So after node concept, we can see the entry loss can be result from both degrader parts and also absorber parts. Here we give two cases. The upward case is for the low momentum case, and the downward side is for the high momentum case. So we can see that for low momentum case, if we set the degrader length to be the red line here, so that we can maximize the stopping absorber ratio, then we can see that almost 98% of the particles can pass through the degrader. As a result, there is no much entries loss in the degrader path. And also, after the particles pass through the degrader, and as shown in this distribution, we can see that this distribution is completely overlapped by the momentum acceptance of the absorber. So it means that we also do not get some entry loss in the absorber part either. On the other hand, if the momentum is getting higher, then it means that we need a thicker degrader length in order to decelerate the particles. As a result, we can see that the result is that the efficiency that the mu minus can pass through the degrader will decay to about 70%. And almost 30% of the entries are lost in the degrader part. And furthermore, see that after this particle pass through the degrader, then the distribution is shown here. We can see that this distribution is also not completely overlapped by the momentum acceptance of the absorber. As a result, we will also get some entry loss in here. So this is the reason why we will get the decreasing tendency of the maxima stopping absorber ratio in the previous graph. Okay, so finally, after we know the reason that causes to this decreasing tendency, then we can try to figure out how to solve it in the experiment. As a result, here we propose a correlation factor equation by using the fitting method of this data point. And then with this fitting method, we can generalize the relation between the degrader length and the stopping absorber ratio. And it is a possible way to fix the discrepancy in a high momentum region. Okay, so in summary, in a preliminary Monte Carlo study, we have seen a discrepancy in high momentum region where we are going to reconstructing the momentum. As a result, we perform a detailed analysis by G4-B9 program in order to study this problem. And finally, we found that the reason that leads to the discrepancy is due to the thickness of both degrader and absorber. So if the degrader is too thick or the absorber is too thin, then there is some entry loss will happen. And finally, we just propose a correction factor equation in order to fix the discrepancy by using the fitting method. Yeah. Okay, so thank you for listening.
Okay, and that's 10 minutes, so thank you very much. And we'll get to the Q&A session. So please, if anyone have a question, just raise your hand in the chat, and I will give you the word.
If not, may I ask a question? I'm
Please.
Osaka from RCNP.
Okay.
Mm-hmm. I have maybe two questions. One is technical, and another one is kind of general. Can you show the either last slide or maybe page, maybe last slide where you show the not the one more before. Yes, here. Here you plot this. Well, page 9, please.
Page 9. Okay.
Right. Okay. So you have two pictures. One, I would naively expect this absorber kind of ratio would be a smooth function as a kind of the length, as function of the length of this degrader. But in the lower plots, it seems they are oscillating. Why they are oscillating?
Oh, okay. Actually, it is not oscillating. It means that if we, for example, if the momentum is 100 MeV, then this is a brown curve. And we can see that for different degrader length, thickness, then the total entries that is stuck in the absorber will be changed. And so we can see a best degrader length that can stop most of the entries in the absorber. Yeah, because naively, if the degrader length is too thin, then most of the particles is not decelerated enough. So most of them will pass through the degrader and also the absorber. And besides, if the degrader length is too thick, then most of the mu minors will be just stuck in the degrader. Yeah. So as a result, there is a best solution for the degrader length and will cause the maximum. Yeah.
All right. General question: do you plan to work as a member of COMET in your future career? What is your plan?
Yeah, I think this topic is somehow interesting, and maybe in the future, because for this semester I only did the simulation work because I cannot touch the real experiments. So maybe in the future, if I have a chance, I would like to see the real experiment. To have a view. Yeah.
I think you are still undergraduate student, right? So a more particular question, would you like to wish to apply for a graduate course of Osaka University, Aoki-san's group?
I'm still
I think that's a totally relevant question, Osaka-san. We better to concentrate to the questions to the presentation.
Okay. Sorry. Yeah, I stopped there.
Okay. So Simon has a question.
It's okay.
Thank you very much for this nice presentation. And I have a question concerning the plots on the 8th slide. And I just wanted to ask whether the results that are presented here are actual measurements for the mu or for the muon, or whether these are simulated by the program of the Monte Carlo simulations.
Yeah, Yeah, it is. All of them is stimulated by the pure Monte Carlo simulation. Yeah, we just generate, for example, 10,000 or millions of events, and then we input to this experiment configuration, and we will see the distribution.
Okay,
and, yeah,
thank you.
The distribution is due to the statistical process, and actually there is some physics behind them. Yeah. So it is embedded in the program. Yeah. So for here we just analyze the phenomena. Yeah. Yeah. Is it okay?
Yeah. Thank you very much.
Thank you.
Okay, and then we have just 10 seconds left. So if there's a short question, otherwise I will thank the speaker and yeah, we'll go on to the next one. Thank you very much.